Hey everyone, and welcome to The Explainer. I'm absolutely thrilled to have you here today because we're about to go on a trip. We are embarking on a fascinating metaphorical journey into the hidden digital postal service that literally powers our entire modern world. We interact with the digital realm all day, every day, maybe even every single minute. But have you ever actually stopped to wonder about the invisible infrastructure making it all happen? Well, today, we're breaking it down step by step to see exactly how your data moves across the globe.
So, I want you to imagine something for a second. Think about the very last time you hit send on a text message to a friend, or maybe when you moved your character in a totally chaotic online multiplayer game. In just a fraction of a second, your action translated into a result on a screen miles, maybe even continents away. It kind of feels like magic, right? But it's definitely not magic. It's this highly orchestrated, wildly complex dance of engineering. And that brings us to our core question. How does your data actually travel across the internet? Well, to understand this modern miracle, we first have to look at the massive problem it was built to solve.
Okay, let's dive into this by directly comparing the old way of doing things with the new. Back in the early days of telecommunications, if you wanted to make a phone call, the network literally reserved a dedicated, continuous physical copper wire just for your specific conversation. If that single wire got cut, boom, your call dropped, period. It was super rigid and honestly highly inefficient. The internet just couldn't scale that way. It desperately needed a modern, flexible solution, something that could survive network failures and handle billions of simultaneous connections. And that solution became the very backbone of the internet we use today.
That brilliant solution is called packet switching. Instead of trying to send one massive file down a single dedicated wire, the data is chopped up into much smaller blocks called packets. Think of it like this. Imagine you need to mail a massive, heavy encyclopedia to a friend. But the post office only accepts standard letter-sized envelopes. What do? Well, you'd tear out all the pages, number every single one of them, put them in individual envelopes, and just drop them in the mailbox. Those envelopes don't have to take the same delivery truck. They travel completely independently, taking whichever route is the fastest at that exact moment. And then, when your friend gets all of them, they just use your page numbers to put the whole book back together.
Let's walk through the actual mechanics of this process. Step 1. Your data, whether that's a picture or a text, is divided up into packets. Step 2, the packets are sent out into the network. And here is the absolute genius part. If a router goes down or some fiber optic cable gets cut accidentally, the network just routes the remaining packets right around the failure. They simply take different paths. Then, step 3, they arrive and reassemble at the destination. And because they take all these different routes, it means packets can absolutely be delayed, dropped, or arrive entirely out of order. Page 5 might literally show up before page 2. So to handle this absolute chaos, the internet relies on some highly specialized delivery protocols.
Let's move to and see how this builds into our next section, looking at our two main delivery careers in the transport layer, TCP versus UDP.
Now, what's really interesting about this slide is how radically different these two approaches to data delivery actually are. Think of TCP as your incredibly careful, meticulous courier. It checks every single detail, establishes a firm connection, ensures the packages arrive in the exact right order, and if a package gets lost, it just says, hey, send that one again. UDP, on the other hand, well, UDP is the hyper-fast, slightly reckless courier. It doesn't bother establishing a connection, it just grabs your packets and basically throws them at the destination's front door as fast as humanly possible. It does not care if they arrive out of order, and it definitely doesn't care if a few get lost along the way. Pure speed is its one and only priority.
So when exactly do we use the careful courier? Well, TCP is the absolute gold standard for web pages, emails, and file transfers. If you're uploading a 20-page final term paper to your college portal, you are 100% using TCP. Why? Because absolute accuracy is infinitely more important than saving a millisecond of delay. You simply cannot afford for a paragraph to arrive out of order, and you definitely cannot afford for the word "not" to go missing from a critical sentence. TCP is there to ensure your data arrives perfectly intact every single time. Now contrast that with the use cases for UDP. UDP is absolutely perfect for real-time audio, video streaming, and online gaming. Think about it. If you're in the middle of a highly competitive online game or a live video call, you only care about what is happening right now. If a tiny packet of data containing just one single frame of video gets lost, you don't want the entire network to freeze up and wait for that packet to be resent, right? You'd rather just drop that frame, maybe experience a tiny, almost unnoticeable glitch, and keep the stream moving so you don't get lag. UDP happily sacrifices absolute reliability for pure, unadulterated speed. But technology is always evolving, so let's check out the VIP Fast Lane Courier on the block, the modern upgrade known as QUIC.
So QUIC is a newer transport protocol specifically designed for HTTP/3, which is the latest version of the web's foundational protocol. What's so brilliant about QUIC is that it actually runs right on top of UDP. It takes the lightning-fast connectionless speed of UDP, but then it builds in its very own error correction. Plus, crucially, it has built-in encryption from the very first handshake. It's essentially the best of both worlds. It offers massive performance improvements for the modern web, meaning your favorite websites load significantly faster and way more securely, right on your phone or laptop.
All right, but a courier is totally useless without an address. Let's shift our metaphor from the delivery drivers to the map makers and traffic cops, IP and ICMP.
IP, or the Internet Protocol, is essentially the digital address system of the web. Just like your house has a street address so the post office can actually find you, every single device connected to the internet, your smartphone, your smart TV, even the server hosting this explainer has an IP address. The Internet Protocol provides the logical addressing and routing required to ensure that every single packet knows exactly where it's going as it hops from router to router across the globe. And this brilliantly illustrates a massive, necessary shift in how the internet works. The older version of IP, known as IPv4, used 32-bit addresses. That gave us roughly 4.3 billion unique addresses. Now, back in the 1980s, that seemed like plenty. But today, with smartphones, smartwatches, and even smart fridges, we literally ran out of internet addresses. So the world is actively transitioning to IPv6, which uses a massive 128-bit address space. To put that into perspective for you, that is enough IP addresses to assign one to every single atom on the surface of the Earth. So yeah, we definitely won't be running out again anytime soon. Next up on our map is ICMP, which stands for Internet Control Message Protocol. If IP provides the addresses, ICMP is basically the digital radar and traffic cop. It doesn't actually carry your web pages or your emails. Instead, it carries diagnostic messages and error reports. For example, if a router gets overloaded and has to drop a packet, ICMP is the protocol that sends a message back saying, "Hey, destination unreachable." And if you're a gamer, you are very familiar with ICMP, even if you didn't know its name. When you check your ping to see how laggy your connection is, your computer is actually using ICMP to bounce a tiny radar signal off the game server to measure exactly how many milliseconds it takes to return.
So the crucial point is this. Billions of fragmented packets route around the globe and assemble perfectly every single second. It is incredibly easy to just take that for granted. We literally tap a piece of glass and expect instantaneous, high-definition video. But beneath that glass is this beautiful symphony of protocols. You've got IP assigning the addresses, TCP carefully ensuring no data is lost, UDP throwing data incredibly fast to keep our games lag-free, and ICMP quietly monitoring the traffic. It's a highly resilient, beautifully designed socio-technical system.
I want to leave you with this final thought. Next time you stream a video, submit an assignment online, or boot up a game, just take 1 second to appreciate the journey. Ask yourself, which invisible paths through fiber optic cables under the ocean and through routers across the entire continent did those thousands of fragmented packets take just to perfectly reassemble on your screen at that exact moment? The internet is an absolute marvel of human engineering, and now you know exactly how it works under the hood. Thanks so much for joining me on The Explainer. Keep learning, keep wondering, and I'll catch you in the next one.